The similarity rules. Centrifugal pumps. The success of this picture as the similarity non-dimensional numbers in pumps correlate pump data leads to a simple rule for comparing pump performance. If pump 1, for example, and pump 2 are from the same geometry family and are operating at homologous point, the same dimensionless position on a chart such as this picture, their flow rates, heads, and powers will be related as follows. For pump 1, and pump 2 from a same geometry family, the rule of the similarity of flow rate similarity three H2 on H1 P second on P1 rho second on rho 1 N2 N1 for the pressure similarity of 2 pump is the same geometry family. These are the similarity rules which can be used to estimate the effect of changing the fluid speed or size of any dynamic turbo machines, pump or turbine within the geometry similarity family. A graphic display of this rule is given in this picture. Showing the effect of speed and diameter change on pump performance for the various diameter and speed. In the first one, the diameter is constant and the change is in the head and BHP in various speed, shaft speed. Speed and diameter change on pump performance. The part A, as I said before, and now the size is held constant and the speed is varied 20%. While the figure B shows a 20% size change at constant speed. The curves are plotted to scale but with arbitrary units. The speed effect is substantial, but the size effect is even more dramatic, especially for power, which varies as D5. Generally, we see that a given pump family can be adjusted in size and speed to fit a variety of system characteristics. Strictly speaking, we would expect for perfect similarity that eta 1 and eta 2 is equal but we have seen that larger pumps are more efficient, having a higher Reynolds number and lower roughness as change ratio. But the larger pump shows better performance, efficiency. Due to higher Reynolds number and lower epsilon and clearance ratio. Two empirical correlations are recommended for the maximum efficiency, one developed by Moody for turbines but also for use pump. It is a side effect, the other suggested by Anderson from the thousands of pump test in a flow rate effect. The Moody relation, which is size change, and flow rate change. This is from the Anderson. The first one is for turbines pump is a side effect, the other such Anderson thousands of pump tests. Anderson formula makes the practical observation that even an infinitely large pump will have losses. He does propose a maximum possible efficiency of the 94% rather than 100%, and also recommend that same formula be used for turbine if the constant change to for turbines. The viscosity also affect on the centrifugal pump are often used to pump oil and other viscous liquid up to 100 times the velocity of water. Liquids heat viscosity one hundred times the viscosity of water. But the Reynolds number becomes low, turbulent, or even laminar with a strong effect on performance. This figure shows typical test curves of head and brake horsepower even versus discharge. Typical test curve versus discharge. High viscosity causes a dramatic drop in head and discharge and increase the power requirement. The ratio of viscosities at 1 and also at this ratio. This ratio shows the more viscous needs more power and also low discharge and head. The efficiency also drops substantially according to the following typical result. For example, for the efficiency leave the water efficiency change with the ratio of and for the 1000 time beyond about 300 of the viscosity of water, the deteriorations in performance is so great that a positive displacement pump is required. The next section is mixed and axial flow pumps, the specific speed and other specification of axial mixed and axial flow.